Okay, I went ahead and fixed that typo. I had a typo in the slide. So we're going to try to do a negative correlation hypothesis test using StatKey. Again, we're using the miles per gallon and horsepower for cars in our car data on my website. We'll be using a 5% significance level, and again assume the data met all the conditions. So again, our alternative hypothesis could be rho is less than 0 or beta 1 is less than 0. So again, we have negative correlation, or what we call an inverse relationship. So that again, that would mean as one of the variables, as weight increases, for example, then as the weight increases, then the miles per gallon decreases. That's what we call an inverse relationship. Okay, so here's the data. This is kind of what the data looks like. I would copy and paste the two columns of data into StatKey. So under StatKey, I gave you would basically go to, under randomization hypothesis test, you'd click on test for slope/correlation. And again, we'd want to put in, if it has a title, we want to click the button that says header row. And here's sort of what it would look like when I go to edit data and I paste in the data. It would look like this. You push OK, and you get a nice little printout from StatKey, right? Nice little scatter plot, has the sample size, the R value, the slope, and the y-intercept. So this is looking much better than the previous example. We notice have our R values getting pretty close to -1. That usually means a pretty strong negative correlation or inverse relationship here, at least with the sample. Our sample slope and our y-intercept, the points do look pretty close to the line, to the regression line. Okay. So when we put that data, if we go to the randomized hypothesis test, we click generate 1,000 samples a few times. Again, when you have it set on the correlation setting, you'll see that the null hypothesis says rho equals 0. That means the computer's going to generate, based on the null hypothesis being that there is no correlation, what kinds of R values would we see? So in other words, this is thousands of R values, 4,000 R values that the computer calculated, and it creates a distribution. And if we're using a 5% significance level in a left-tailed test, we can put 0.05 in the left tail, and we see that our critical value for our R was -2.271. And again, if you were doing a traditional program like StatCato, it would give you that critical value. But this is a nice picture of what's going on. Now, what we want to know is our actual sample correlation coefficient, the real R, is that in the tail. Our real R was -0.903, which is definitely in the tail. It's definitely in the left tail. It is to the left of that critical value, -0.271. So again, that would mean that the sample data significantly disagrees with the null hypothesis. But you could also calculate this with the slope. So if we clicked it on the slope setting in StatKey, notice the null hypothesis changes. You get beta 1 equals 0. Again, that still means no correlation, right? No. So again, but this time the computer is basically calculating thousands of samples and calculating thousands of sample slopes and putting them all on the same graph. Now again, if we click left tail and 0.05, we get now a critical value for the slope. It's important to know what setting you're on, because if you're on the slope setting, you have to use the sample slope, and if you're on the correlation setting, you have to use the R value. So in our case, this is on the slope now. So we see that our left tail starts at -2.516, and our actual sample slope was -8.372, which also falls in the tail. So really, you get the same information if you based your simulation on slope or if you based your simulation on the R values. Calculating the p-value, we can again remember the p-value is the probability of getting the sample data, or more extreme. If we're dealing with the correlation setting, then we should put in the actual sample correlation coefficient R, which was negative 0.903 in the lower left box. And if I do that, I'm way in the left tail and I see I get a 0 p-value, so approximately 0. I could also do the p-value calculation from the slope screen by putting in the actual sample slope, negative 8.372 in that bottom box, and again I get the same p-value, 0. So you don't have to do both. You can do the calculation based on the R, or you can base it on the slope. One thing to keep in mind, if you are going to calculate the t-test statistic, which again is that sample slope minus 0 divided by the standard error, take a look right here. This graph actually does show you what the approximate standard error was, about 1.538. So that would be, if you wanted to do like a quick calculation of what the t-test statistic might be, you could, but you'd want to use the standard error based on the slope. So this one right here says 1.538. Okay, so what's our conclusion? Of course, the sample slope and sample correlation coefficients both fell in the tail. So our sample data significantly disagrees with the null hypothesis. Our p-value was 0, so the sample correlation coefficient and the sample slope are unlikely to be due to sampling variability or random chance. Again, if we have a low p-value and we're assuming we met conditions, then we should reject the null hypothesis. This is significant evidence, right? So our conclusion, again, would be if we reject the null hypothesis, but our claim was the alternative, we should have a conclusion of there is significant evidence to support the claim that the weight of a car and the miles per gallon have an inverse relationship. This would tell me, by the way, also that the regression line formula would be a good model for estimating miles per gallon based on a car's weight. So that's kind of what that tells me. All right, well, thank you again. This was Matt Touchot with Intro Stats, the Quantitative Association Test examples.